In section 1.2.5, now we will discuss the curl of a physical quantity or the curl of a vector or function or field. Now the curl gives us the rotation of a vector, like how much a vector is curling or rotating. Some will curl more, some will curl less, and the curl is now a vector quantity because the curl is always taken of a vector quantity, and as it is a cross product, so this cross product tells us that the result of it will be a vector quantity. Like this is a del operator and this is the cross product, and we are having vector v, so this del and cross together we call is curl. It gives us the rotation or the sweeping or the curling of a vector quantity. Now if we are having a vector v such that it is vx, vy and vz, a three-dimensional vector, then the cross product, we know that how we will write it. I'm not writing the vector again, but we know that a cross product is always written like this in a matrix form. This is xyz, and then del operator is curly by curly x, curly by curly y, and curly by curly z. Similarly, it will be vx, the components of this vector vx, vy and vz, and if we expand this one, then for the x component we are having the product of this, like curly by curly y and of vz minus curly by curly z of vy. Similarly, the next will be minus, and it is minus y component, and y will be then x and vz, so curly by curly x and vz minus curly by curly z and vx. Similarly, the third component, the z-axis, it will be curly by curly x and y, curly by curly x and vy minus curly by curly y and vx. So this is the expansion of del cross v. And now to understand this one, we will go to some solution of example, and this is example 1.5 in your book. And this example is saying, but before going into the example, let's note that if the right hand rule, for example, if curling is like this, then it will have its direction upward, and curling this way, the direction will be downward. So curl will also give us a magnitude like 1, 2, 3, but a direction will be associated with this one. Now suppose we are having some let me draw some diagrams, and then we will write the functions for it. For example, we are having a coordinate system like x, y, z here, and then the functions is like on this one. Let's say we are having x, y, z is our coordinate system. This is x and this is y, and here we are having the z-axis. Now this is the origin, and the vectors are such that they are curling like this. And first, let's say, let me do the representation, second, and then the third, like this. They are curling like this. And let me now draw the vectors here in order to represent this one. For example, this vector curls like this. Similarly, it will be a bigger vector, and this will be a further bigger vector, and then a short one here, and then here, and here as well. Similarly, here and here, and we have here the vectors, they are curling like this. Now if I look at this vector, then this is in the x and y plane, like the vectors are in the x and y plane. Now if I take any vector here, for example this one, it is in the xy plane, so it will have a y component which is parallel to the y-axis, and the x component which is parallel to the x component. So these are the components of it, and I can write its vector form like this is a vector VA, and VA is a two-dimensional vector such that this is equal to minus y in the x direction and plus x in the y direction. Now, if I look at this one, then in the x unit vector, it is along this direction, and we are having this magnitude is in opposite direction to the x-axis, because x-axis is in this direction, y-axis is in this direction, and z-axis is in this direction, while this vector is going in the opposite direction. So it is y magnitude in the minus x direction, while plus x magnitude in the plus y direction. So this is a vector that we are having. Now I want to find out the curl of this vector. So its curl will be equal del cross VA, and this is equal, first we have the x component, so this is the x component, and now curly by curly y of the z component. So it doesn't have a z component, so we are having 0 here, minus the Vy component, and the Vy component is equal to x, and its derivative with respect to z will give 0, minus we are having the y component, and then the z component, it is not here with us, we are having a two-dimensional vector, then minus, and then vx component, the minus y is the vx component, and it is with respect to z, so this will also give 0 here, plus z axis, and then the z component, we are having the vy component derivative with respect to x. So this is the vy component, and its derivative with respect to x will give us 1, and then minus the vx component with respect to y. So this is the vx component, which is minus y, and its derivative with respect to y will give minus 1. So that minus 1 and this minus 1 will become plus, and we are having the result of del cross VA is 2 times the z unit vector. So we can say that as it's a two-dimensional curling, and the two-dimensional curling, and it's in the xy plane, so it will be in the z-axis, like xy plane here, and this is the z-axis, and we are having the curl of this vector VA is equal to 2 in magnitude and z in the direction. Z unit vector is the direction of this. Similarly, in another figure, we are having a two-dimensional setup, and it is such that this is VA, and we are having now VB, and VB is such that, let me draw the diagrams first. This is our one axis, this is another, and here we are having another axis which is like this. This is our x-axis, this is the y-axis, and this is the z-axis. Now the vector field is such that it is just the translation of this x, like they are going in this direction. And then returning in this direction. So it's like a two-dimensional setup, going this way and then coming back this way. And finally we are having one like this. And now this is the vector form of this is v of b is equal to, this is actually the movement of x along the y direction. So we are having x which is moving in y direction. And now we will find the curl of this vector. So this is del cross v b here. And now again I will first write the x component. Now it is having only y component, so this one, the z component is 0 here, minus. We are having the y component, but it is x, and with respect to z its derivative will give us 0, then minus y component, and here it is having no z component and it is having no x component, so this is 0, and then the z component here, and we are having the vy component, so it is having a vy component and its derivative with respect to x will give 1, and then minus, we don't have any x component, so it is equal to 0, and this vector curls comes out to be in the z direction only, and its magnitude is 1. So it is the x going this way and then coming back this way, and this is the z direction. Let's say it's going this way and then returning this way, and as this is one dimensional, so we are having 1 is a magnitude here. Now the curl is very important from the point of view of electrodynamics, because from the curl we are having the two curls, very familiar curls, the curl of E and the curl of B, a curling electric field and a curling magnetic field. What will be those curls? And keep in mind one thing in both of these, that in both of these the charge will be in motion. The charge will be not static. These are not electrostatics. Otherwise we will have some other equations like del cross E will then be equal to 0. At the moment I'm not going to discuss del cross E or del cross B, but giving you the importance of this curl to understand this curl in order to interpret our equations or write our equations clearly, and explain most of the electrodynamics. Then we are having some second derivatives. Second derivatives is not that important topic that I started as a separate, but let me write here is 1.2.7, and this one is the second derivatives. It actually tells us that how, if the double cross dot or gradient comes in, then how it will be. For example, the very first one, let's say we are having the divergence of gradient, like the divergence of a gradient. So gradient will be of a scalar function, and this scalar function is t. So the divergence of gradient, and it will give us some number, because the divergence will always be of a vector quantity, and now this gradient t is a vector quantity. Now gradient is giving us the maximal change in t in a given direction, and that's why it's a vector quantity. And then how much it is diverging, so it means that this thing will be not equal to 0. We will get some result out of here. And then we are having the second is the curl of gradient. Now you think that gradient is something which is a directional change. So it will be change in a certain direction, means it is going one way. It will never curl. It will diverge, but it will never curl. And that's the reason that the curl of the divergence will always be equal to 0. When it's a gradient, and its curl will always be equal to 0. And then gradient of divergence 3. We are having gradient of divergence, like the divergence of a physical quantity or vector, that is v, and then the gradient of it. So it is also legal to have this thing, because the divergence of v is a scalar quantity. It will just be a number, it will just be a scalar field, and then how much is it is changing in a given specific direction, unique direction, then it will give us non-zero thing. It will not be 0. It is meaningful to have this thing. Then divergence of a curl. So 4 is the divergence of a curl. So it is meaningless. Look here, that if we are having a vector v and it is curling, and then of that curling thing you take the divergence, then it is meaningless. Means it will never diverge, because it is already curling. It means that this thing will always be equal to 0. And then we are having the curl of a curl. Fifth is the curl of a curl. So it is meaningful, because this will give us the curl of vector v, and then that curl we can further find out a change or a curling effect at that one. So it is meaningful as well, and this will give us some positive result, or it is a very familiar identity. Now if I look to this one, then is that we had the scalar triple product A dot B cross C, and it was giving us the volume of that space. It is meaningful, because this is not the variation, but B cross C forms the base, and then it is then shifted with A dot. So it gives the volume. This one is not giving the volume, because it's a variation, it's a gradient. And similarly, we are having the cross product of 3 vectors, and cross product of 3 vectors is not giving us a volume, but it is means the rotation of this vector along this vector, and then there is the rotation of their resultant along this one. So this is a Bay-Cave rule, and this is meaningful. And here in the curl, this is meaningful as well, but this is not a vector triple product. It is another identity, and this identity is equal to del the gradient of divergence of V minus del square V. We will discuss the del square in coming lectures. It's called the Laplacian, and it is the del dot del, like the two dels when you multiply, like the gradient and the dot product between two gradients, and this will be equal to curly square by curly x square plus curly square by curly y square plus curly square by curly z square. So it is a double differential partial differential derivative. We define this with del square, and we call this is an operator, while the operator is after Laplace, and it is called Laplacian. So this is another thing that we have. Now in the coming lectures, as we are done with the differential calculus, in the coming lectures we will start with the integral calculus. So we will discuss the path integral, the surface integral, and the volume integral. And then we will move to the fundamental theorems of gradient, divergence, and curl.